thank you very much for the introduction. I'm very glad to be here. I always say, well, always since a week ago, say that the hometown ETH conference is the best ETH conference. So yeah, I really like ETH Zurich, and so it's very nice to have an excuse to get our friends together and to meet each other. So as she said, my name is Aisling. I work at a company called Tatseo. We build MPC stuff. We do a lot of protocols for zero knowledge. And today I would like to introduce you to a small piece of tech called co-SNARKs or collaborative SNARKs, which opens up this whole new kind of corner of Ethereum, blockchain, Web3 called private shared state. So before we kind of dive into it, have any of you already heard about collaborative SNARKs? Okay, actually quite a few, nice, okay. Then for the rest of you, do you know about multi-party computation? Okay, actually not bad. And then zero knowledge proofs, I guess, is probably the one that most people in the room should have heard of. Okay, great. So not bad. Okay, then it's nice to gauge because then I can tell you a bit more detail. So I want to kind of give you a bit of motivation for private shared state. I want to then kind of introduce co-SNARKs as something that can actually enable this private shared state. I want to then talk about how we actually take this sort of co-SNARK idea, how we actually implement it, how we show that this is a reality in practice, and then a bit kind of the future of privacy. And so what is private shared state and why do we need it? So one thing that I find interesting about this world, and like as the blockchain sort of ecosystem and industry develops, Ethereum kind of started and like gave us this public shared state. And as it develops now, we start to see these kind of new state models arising. And I find this kind of interesting because yeah, when you have new types of data models, there's like all types of economies that can be built around this, so it's pretty interesting. But yeah, at the beginning, Ethereum gave us this public shared state. You had this kind of state transition machine that would take some data, change its state, move it around, like you could then build smart contracts, you could do stuff with this data, this is how kind of DeFi evolved, all this kind of stuff. And this was great, and like having everything public meant that everybody could look at it, everybody could verify it, and this was like one of the coolest things about about Ethereum. But then as people started to actually build stuff on top of this state and on top of this data and build more stuff and more stuff, it became a bit not so efficient, let's say. And then I guess you know, if you know about ZK at all, that ZK rollups came around to help scale Ethereum. This was great because now all of a sudden we have like much faster ways to do DeFi, much faster ways to do general stuff with state on blockchains. But then, you know, there's kind of this issue of privacy. Now we're actually putting our lives on blockchain, and this is kind of not so ideal if everything is public. And one of the cool things, as I said, about Ethereum was that you have this public verifiability, which is great if you're trying to like take down the banks or if there's like entities or institutions that you don't trust. But for individuals, like in their day-to-day life, is it needed that like all my colleagues verify all my transactions? No. So like it's super nice to have privacy for an individual. Then given that we're in this situation where there's zero knowledge rollups that were used for scalability, now we can start to actually use them for the zero knowledge property that they actually were developed for in the original place. And so yeah, these zero knowledge rollups kind of advanced, gave us the tools to have privacy, and now you see the emergence of things like Aztec and Elio, Maiden, Midnight, these sort of either L1s, L2s, whatever, ZK-based privacy chains, blockchain stuff. And so now you have these two-state models. You have this sort of public shared state of Ethereum where everything, like there's all this data, everybody can see it, everybody can verify it. And then you have this other side where you have this private data. It's either in your phone or it's encrypted. And there's some sort of disconnect between the two of these. And I think, so what we try to do is to bridge these a little bit. So yeah, like the public shared state gave this composability, which was great, that we could build on top of it. The private state is great because now we as individuals can have privacy and we can build all these cool ZK apps and whatever. But the limitation is that all this nice composability and all this nice stuff that we could build, like with Ethereum, goes away if you start breaking these pieces of data into silos again. And so the dream is to then sort of try to bridge these two things, again, like be able to use the private state, be able to use the public state, be able to build stuff on top of both and use different pieces when you want. And so this is what we call, or what is kind of being emerging in the industry now, is being called private shared state. So it's not just public, it's not just private shared state. And so the reality of this, so this is the dream that we want, that we feel like opens up this whole new part of the industry that is completely untouched. The reality is that, okay, if you want to actually start doing stuff on encrypted data or on private data, if you want to do stuff on public data, if you want to mix these things, you need to be very careful, obviously. And then you end up in this world of computing on encrypted data. So what is the state of that at the moment? Well, there's ZK, which is great. You can do a lot of stuff with ZK. You can make proofs, you can verify stuff, you can attest to things. But the problem with ZK is that you're just proving sort of relations about things. You're not doing any functions on this stuff. Like, so if you have any data where you want to do some matching, or if you want to do, I don't know, compute any sort of function on this private data, ZK is limited in its functionality for this. So it's not really possible to do like a lot of computation, let's say, with ZK. It's just for proving relations. My name is Aisling, I live in Switzerland, this kind of stuff. It's not like, how many people in the room's name starts with A? How many people in the room live in Switzerland? So this kind of stuff cannot be done with ZK. Another sort of like hot topic over the last, I guess, 10 years, depending on if you're in the research side more than the industry side, but is homomorphic encryption. And this is cool in the sense that you can encrypt your data, send it off somewhere, you can compute functions on it, you can get the encrypted result. This is great. Like, but is it actually practical? This is like a super cool thing. Like there's lots of nice properties. The trust assumptions are low. It's great. But it's super impractical for real world stuff. Like there are demos where, yeah, maybe you can do a little game if you spend like hundreds of thousands of dollars on like very beefy machines. But yeah, for real world stuff, it's not so practical. Another technology is multi-party computation. So a few of you in the room said you knew about this already. And this basically, instead of like me encrypting my data, sending it to one person or a cloud or whatever, and computing over that, you split it over different people. So you kind of end up with this secret shared data over multiple people, and then they do computation and it comes back together in the end. This is practical for like highly specialized protocols. So you saw DC from World, he talked about MPC. They do probably the most practical MPC. We work together, but they do like, it's like the most practical large scale deployment of MPC. But again, it's like highly specialized protocols. So yeah, it's kind of, it's definitely more practical than homomorphic encryption. So this is where we go. TEEs are hot now. I think you saw the last guy talking about this with AI. Great, you can do like secure computation, but then you don't get this shared part. Again, you're back in these data silos. So with a TE, the data is normally on your phone or on a device. You lose this shared state. And this was the whole nice point of Ethereum and building composable stuff. So surely there's something that can be done like either between all these or something else. And then, yes, we enter collaborative SNARKs. And so collaborative SNARKs are basically, if you combine MPC and ZK. So basically you want to do a zero-knowledge proof, but in MPC. So zero knowledge was nice because we had all these verifiability properties that we like from Ethereum. We had the privacy side, but then we didn't have the computation. If you now take the zero knowledge with all its nice properties and you put it into this MPC environment, you get the computation on top. And so this is how to collaboratively compute a proof, basically. And so this emerged in 2021 from Dan Bonnet and his PhD student, Alex. They wanted to collaboratively compute proofs without revealing the witness. So I think at the time there was like some different uses where, let's say, I am generating proofs on my phone. It's maybe like limited in its power, like a small device or whatever. And I then start to want to, it's becoming too much for my phone. I want to outsource this proof generation. How can I do this by still maintaining privacy? They introduced these co-SNARKs to do this. And so the approach was to run zero-knowledge provers in an MPC environment. Quite simple, I think. They use techniques like standard techniques from the MPC world, so secret sharing and MPC, to maintain the security while you're doing computation, to maintain privacy while you're doing things. And then they also leverage the MPC friendliness. So this is something maybe more for like the research side of the room. MPC friendliness of provers for practical implementation. So this means that there's like some parts of ZK that are very linear, and it's very easy to compute them like in parallel. So you can split them across different machines. You can compute in parallel. And then you have like a little minimal overhead of communication. So this is one of the nice things about it. And so it makes it that, like, when I said for large-scale real-world use cases, if you have highly specialized MPC protocols, it's good, it's efficient. But if you want to compute zero-knowledge proofs, actually MPC is like a super nice practical tool for doing this. And so how do they work? Yeah, like if you know just a small picture, so for a zero-knowledge proof, normally you have a witness, so some secret data that you're trying to make a statement about, make a proof about. Yeah, you give this to a prover, he produces a proof pi, and then you send this proof pi to a verifier, he verifies. And so with the co-SNARK idea, you're saying, okay, I don't just have one witness anymore. I either split it in three, or I have data from different people that I'm trying to prove some statement over. And so, yeah, I have a multi-party setting where there are, for example, 3 provers who collaborate together on private witness data and produce a proof which is sent to the verifier. And I think one of the important things to note here is that the verifier is the same across both scenarios. So like a proof is a proof and can be verified by anybody. So it doesn't need like a whole new tech stack. Like all the like ZK verifiers and all the ZK stuff that we had from before can be used in this setting. So it's nice. You don't have to redo everything. You don't need to learn new stuff. You don't need to develop like a whole new stack. So this is cool. How about implementing them? Okay, so we say, yeah, it would be nice to have this private shared state world where we can compute on private data. We still have verifiability. Okay, now there's this co-SNARK idea that came from these academics. Is it actually practical? Can we do this in the real world? And the answer is essentially yes. So as I mentioned before, like zero knowledge is like the main sort of heavy computation is linear. And so secret sharing introduces no overheads to this. So you can split the witness data across different compute nodes, node providers, whatever. And you can do MPC, like you can generate a proof very easily with like little overhead. So the main proof systems like Growth 16, Planck, these are quite MPC friendly. So it means that, yeah, you introduce very little overheads if you want to do Growth 16 proofs, let's say, in an MPC environment. Planck is less friendly than Growth 16, obviously, as it's kind of more versatile, it's more robust. It's still efficient, but yeah, it's not as efficient, but you still get a lot more functionality. And so, yeah, like, this works really well for elliptic curve-based provers. So I think there's some people in the room who worked on hash-based proof systems, and there, MPC is not so friendly, let's say. So how about writing circuits? So yeah, like as I said with the verifier, you want that you don't have to rewrite the whole ZK stack. So we basically took the kind of most commonly used languages for developing zero-knowledge proofs. The main one is, well, the easiest or the easiest place to enter the ZK world is via CIRCOM. And so we added functions to CIRCOM that allows it to be allows you to generate SNARKs in a MPC environment. And so with these extra functions on top of CIRCOM, we got co-CIRCOM. So there's collaborative CIRCOM. And in CIRCOM, we adapted Growth 16 and Planck provers to work in an MPC environment. And so then this gives you like a feature-complete co-CIRCOM. The other one, like emerging DSL, I saw somebody, I see a Noir shirt in the audience. So there's an emerging DSL called Noir, which is quite hot right now. We sort of took a bet on this as like the kind of cool new language that is emerging to develop ZK circuits, applications, everything. We really liked it, and we were implementing some crypto libraries in Noir. So we ended up then now taking Noir as the sort of next library after CIRCOM because it's the more widely used, we expect. And so yeah, we, like with Circom, we added some functionality, some functions to Noir to get CoNoir. So yeah, we adapted the provers that they use to work in MPC as well. There is a QR code if you want to get to the repo where all the stuff is there. You can play around. So where are we in practice? So I'm saying, yeah, hey, we want private shared states. Hey, we have an idea of how we might achieve this. Hey, actually, we can implement it. Does it work? Is it the case? Is it like FHC where we're like, okay, it kind of works, and like maybe in 10 years it'll be practical? But yeah, like it's here now. So the goal is generally to generate proofs with as little overhead as possible. Compared to a single prover. So you're going from the single prover to a multi-prover setting. And the reality is pretty sweet, actually. So I think this is not so visible on the screen, but this chart shows basically that like the multi-party provers have like little to no overhead against the single-party provers. And even like this top line you see is a little bit lower. It's even, so like the multi-party setting is even a little bit faster simply because we use Rust instead of JavaScript for these things. So it's there, it's practical, there's no overheads. Actually, this is kind of no overheads in terms of computation. So yeah, it works, it's practical, it's great. Have we actually deployed anything? Yes. So last year we did some demos. There was a Max Pick Challenge, which was a game basically. It was a guessing game where, let's say, everybody in the room guesses a number. We all encrypt our number. We secret share it to a network. Then we do an MPC computation over all these numbers and choose the biggest. So you have your private guesses, and you do some computation over this to get the biggest. This was the first sort of private shared state game. And we also did proof outsourcing at DevCon. If you saw anything with the Cursive guys, they have these NFC wearables, and they were outsourcing because they have an application. And again, it's a phone-based app that people were using or in the browser. And there, again, as more people were using it, the proofs were getting bigger and bigger. And again, they wanted to outsource. But their focus is very much on privacy, so they wanted to outsource while maintaining privacy. So we worked with them to do this proof outsourcing where they were sending their witness encrypted secret sharing to our network, and then we generate proofs on this. But the bottleneck is actually one of the things, I don't know if like even from the like traditional world, like the traditional tech, like Web 2 world, people like to use MPC because it allows you to sort of break out of this data silo that you're in, and you can learn some stuff, maybe aggregate statistics or whatever. And people tried it then in the old world, in the Web 2 world. And people are also interested in it. Now you see like there is actually a need for this. And still people are not using it so much. And so one question is like, why? What is actually the bottleneck here? And I think it's actually, like what we found is that people are not interested in building and deploying their own networks. And like this makes absolute sense. You're like, okay, hey, I want private computation. I'm building my ZK app, whatever. Why should I be the one to also like then deploy, find node providers, write this secure network, all this kind of stuff? And so, yeah, there's kind of no real MPC network that people can just like outsource private computation to. So now we start to build this basically. And in DevCon, we had the first sort of AlphaNet version where we did these first production co-SNARKs for Cursive I mentioned earlier. Yeah, private proof delegation. And so this generated about 40 proofs per minute, whereas otherwise they were doing about, I think, one proof every 10 seconds on the phone. So it turns out that it's practical, they get more proofs, yeah, and they can outsource their private computation. So now the goal is basically to extend this network, keep it on all the time. So if you're interested in talking about private computation, you can find me or some of my colleagues here. So looking ahead, let's see how much. It's still a very new and emerging area. It's all like, there's really a lot to be discussed, decided, like what is even this stuff called? Is it ephemeral? Yeah, there's really a lot to be decided, and it's very cool, I think. It serves a purpose. So like whenever like this new tech emerges, people often ask like, what's the use case? Or is this like tech for cool tech's sake? Or like, is this actually needed? And the nice thing about co-SNARKs is that they arose because there is actually a need that they need to solve. And so this was really cool. I like this. I mean, it's useful. And so yeah, the main uses are these private proof delegation, where you want to outsource your proof generation to somebody else while maintaining privacy, and then the kind of more broad computation for a private shared state. Networks are in the works. We're working on it. So it's kind of emerging. If you want to play with them, let us know. There's many open problems. So MPC, like when you gain this efficiency over FHE, for example, you introduce some trust assumptions. It's like you don't get this for free. And so there's this collusion issue, which is some trust problems. Maybe there are mitigations for this. You can run in TEEs. You can try to do some economic stuff, slashing, whatever. But this is very much an open problem. The efficiency is a huge problem still. Like it works, like we're doing it for cool stuff. World is doing great stuff. Like the proof outsourcing is fine, but like it needs a lot of effort. And also variety, like so the functionality is still quite not limited, but like, yeah, we don't have the full range of everything. So yeah, let me know if you want to experiment. What would you think? Yeah, so like for me, this private shared state thing, like what I really want to get across is that like this is a huge area of blockchain, of Web3 that is like completely untapped, like 0% usage here. And so it's a bit like if you're sitting in 1990 and someone says, look, e-commerce is coming, and you're like, what? Like, how can it be? I don't understand why you want this digital stuff. I can just go to the store. And you're like, yeah, but like it can be so much bigger than just going to the store. So yeah, it's a huge thing that is coming. People ask, what is the use of blockchain? So again, we talked about the usefulness of stuff. With blockchain, what's the use case of blockchain? Why do we even need it? You can just have a distributed database, whatever. For me, this is it. Like privacy in Web3 is the one thing that Web2 literally cannot do because they're centralized. So for me, this is the point of blockchain, basically. So yeah, if we trust the institutions, high security stuff is solved. Like if you trust Google, if you trust the banks, whatever, problem solved. But the thing is we don't. And like also for, again, our personal data, for our individual stuff, our social spaces, these are not secure. Like Facebook can see your stuff, Google can see your stuff, YouTube can see your stuff, and they can steer you in different directions. So yeah, privacy is needed. And that's it for me. Thank you very much.